Today, we're diving into a true hidden gem of mathematics, a formula so elegant and so beautiful it's been called the e to the pi I of the mathematical community. This thing should be right up there with E equals mc squared, but most people have never even seen it. So, what is this hidden masterpiece?
That's Grant Sanderson from the amazing channel 3 Blue 1 Brown, and his quote just perfectly sets the stage. We're back to uncover something that describes a concept you probably learned about back in middle school, the volume of a sphere. Sounds pretty simple, right? But trust me, the magic and the real beauty, well, that all happens when we start to generalize this idea, when we start asking about spheres in dimensions way beyond our familiar 3.
So what could possibly be so beautiful about something we can't even visualize? I mean, really. And that's the mystery we're going to try and unravel together. It turns out this really abstract idea has some surprisingly real consequences, and it leads to one of the most counterintuitive and absolutely stunning results in all of mathematics.
First things first, why should you even care about higher dimensions? I know, they sound like something straight out of sci-fi, but believe me, they are super real and incredibly useful, and we can see exactly how with a simple little puzzle. Okay, so check this out. Imagine you pick two random numbers. Let's call them x and y. What's the probability that the sum of their squares is less than or equal to 1? Now thinking about this geometrically makes it so much easier. As you can see, your two random numbers just define a random point somewhere inside this square. And the question? It's really just asking for the probability that that point lands inside the circle. That's it.
So get this. The answer is always just a simple ratio, the area of the circle divided by the area of the square. And the amazing part is, this works in any dimension. So if you pick, say, 100 random numbers, the probability that the sum of their squares is less than 1 is simply the volume of a 100-dimensional sphere divided by the volume of a 100-dimensional cube. Just like that, this abstract geometric question becomes this powerful tool for understanding probability.
And this isn't just some clever party trick. High-dimensional geometry is quite literally the language of modern technology. When an AI like ChatGPT processes language, it's basically turning words into coordinates, points in a space with, like, hundreds or even thousands of dimensions. Understanding the geometry of these spaces, as you can see here, is absolutely critical for the AI, cryptography, and the physics that powers our world today.
Okay, so we've established these spaces are useful, but as we start to venture into them, our everyday common sense intuition is going to break down. And I mean, it's going to break down spectacularly. Let's try another classic puzzle just to see how wonderfully weird things get. All right, take a look at this setup right here. We've got a square with circles in each corner. The question is simple. What's the radius of that small circle right in the middle, the one that just kisses all four of them? In 2D, the math is pretty straightforward. The radius is the square root of 2 minus 1, which is about 0.4. Seems totally reasonable. The logic is just to find the distance from the very center to a corner and then subtract the radius of that corner circle.
And the cool thing is, this logic, it generalizes beautifully. As the slide shows, it's a simple two-step process in any number of dimensions, which we'll call n. Step 1, the distance from the center to any corner is always just the square root of n. Step 2, we just subtract the corner sphere's radius, which is always 1. So that gives us our final result. The radius is the square root of n minus 1. Simple, right? So, let's plug in a bigger number and see what happens. In 10 dimensions, the radius of that inner sphere is the square root of 10 minus 1, which comes out to about 2.16. Now, just look at that number for a second. You might just be nodding along, but really think about what that number means.
Remember, the box itself, it only goes out 1 unit from the center to the middle of each side. But our so-called inner sphere, it has a radius of over 2. I mean, that means the sphere we thought we were tucking neatly between the corners is now so ridiculously big, it's literally poking out through the sides of the box. Yeah, our intuition is officially broken.
Now, what's really fascinating here is that this doesn't mean high-dimensional spheres are all spiky or something. They're perfectly round by definition. No, the problem, it's the cubes. Cubes are just messed up in higher dimensions. The corners of a cube get incredibly far away from its center compared to its faces. Cubes are the weird ones here.
So, our intuition has totally failed us. We clearly need a more rigorous way to navigate these strange new worlds. And that brings us to the formula itself. And the logic behind it? It's shockingly clever. It basically involves thinking like a knight on a chessboard. Let's start with what we know. As this chart shows, we've got the formulas for the interior, or volume, and the boundary, or surface, in 1, 2, and 3 dimensions. Now look closely here. For any of you who remember your calculus, you might spot a pattern. If you take the derivative of the volume formula with respect to r, you get the boundary formula. That little relationship? That's our first big clue. And here it is. This is the brilliant insight that goes all the way back to Archimedes. He found a way to calculate the surface of a 3D sphere by connecting it to the volume of a 1D sphere. On our little chart, this is like a knight's move. We go down one dimension and then over to the other column. The core idea is basically a clever way of unwrapping the higher dimensional surface so that we can calculate it using a lower dimensional volume. It's an absolutely incredible shortcut.
So what this knight's move gives us is this really powerful tool. It's called a recurrence relation, which you can see right here. I know, sounds fancy, but it's just a simple rule that lets you get the next answer using the ones you already have. To find the volume constant in any dimension n, we just take the constant from 2 dimensions back and multiply it by 2 pi over n. That 2 pi part, that's the engine of our knight's move. It's what lets us jump up the dimensions. And dividing by n, that's the calculus step, basically, of getting back from the boundary to the volume.
And this right here, this single, elegant rule, this is it. This is what unlocks the volume for a sphere in any dimension we can think of. 4, 5, 100, 1,000, it doesn't matter. The path is now perfectly clear.
Okay, so we've got the tool. Now let's actually use it. We're going to calculate the volume of a sphere with a radius of 1 and a bunch of different dimensions and plot the results. And this is where the story takes its final, absolutely mind-bending twist.
All right, so in one dimension, the volume is 2. Easy enough. In 2 dimensions, it's pi, about 3.14. Then in 3 dimensions, it's 4/3 pi, so around 4.19. So far, so good, right? The volumes are going up just like you'd expect.
Okay, let's keep going. We move on to 4 and 5 dimensions, and yep, the volume is still growing. A 4D sphere is about 4.93, and a 5D sphere, that actually peaks at around 5.26. But hang on, look at how it's growing. It's starting to slow down, isn't it? Something is about to happen.
And here it is. In 6 dimensions, the volume actually shrinks back down to 5.16. In 7 dimensions, it's down to 4.72. Can you believe that? After peaking in the 5th dimension, the volume of a sphere just starts getting smaller.
And this isn't just a little dip either. This is a head-first plunge straight towards 0. But why? Well, think back to that rule we found, that recurrence relation. We're multiplying by 2 pi, but we're also dividing by n, the number of dimensions. It's like a tug-of-war. And right around dimension 7, n gets bigger than 2 pi, and division starts to win. The volume just collapses.
Just how dramatic is this collapse? Well, let's take a 100-dimensional unit sphere. Its volume is, well, it's basically nothing. I mean, 10 to the negative 40? That is an absurdly, incomprehensibly small number. All of that infinite, high-dimensional space, and the sphere right in the middle of it contains pretty much 0 volume. Wild.
And that, right there, is the beautiful, bizarre truth about high-dimensional spheres. It's a journey that starts with a simple little probability puzzle, forces us to completely abandon our intuition, and then ends with a revelation that just feels impossible. And it really makes you wonder, doesn't it? What other simple, familiar ideas that we see every day are hiding this kind of deep, profound beauty, just waiting for us to dare to look at them in a totally new light?